All right, BC Calculus, this is topic 57, Introduction to Series Part 2. A lot of this is probably not going to be tested this year, but I wanted to go ahead and cover it anyway, and there's a few things on here just to review that are stuff that is covered as well. So what does series have to do with calculus? That's always a big question. So the biggest thing is that, remember, these are approximations of known series. So because they're polynomial approximations, we can do algebra on them, like substitution. We can also do derivatives on these, and we can do integrals on these as well. Okay. So one of the series that in a normal year you would have to memorize is the Taylor series for e to the x, which is 1 plus x over 1 factorial plus x squared over 2 factorial plus x to the third over 3 factorial dot 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 dot, plus the general term would be x to the n over n factorial, because you can just go with the pattern here until you go out to n, where n is any number. Again, it would be a summation as n goes from, in this case, 0 to infinity, would be what this series would look like if I wrote it out in summation notation. Okay, so this is the Taylor series polynomial that approximates e to the x. So since it's a polynomial, can we integrate it? Yes. Can we differentiate it or take the derivative of it? Yes. So what is the derivative of this Taylor series? So the derivative of 1 is 0, plus the derivative of x is just 1 over 1 factorial, which is just 1, so it's just 1, plus the derivative of this would be 2x over 2 factorial, and then the derivative of this using the power rule would be 3x squared over 3 factorial, and again the factorials are staying on the bottom because they're coefficients. Technically this is 1 over 3 factorial. And then plus, this would be 4x to the third over 4 factorial, plus 5x to the fourth over 5 factorial. Okay. And now if I simplify that, I don't have to write 0, so I'll just start with 1 plus 2 factorial is 2 times 1, which is 2, and that would cancel that 2 out, so it just gives you x. And then 3 factorial here would be equal to 6, because it's 3 times 2 times 1, and 3 over 6 gives you 1 over 2, so that would be x squared over 2. And then 4 factorial is 4 times 3 times 2 times 1, which is 24, and 4 over 24 gives you 1/6, so x to the third over 6. And 5 factorial is 120, because it's 5 times 4 times 3 times 2 times 1. 5 over 120 reduces to 1 over 24, so that'll be x to the fourth over 24. And then when you work with factorials, you should notice that this 2 on the bottom you can write as 2 factorial. And then 6 is 3 factorial. And 24 is 4 factorial. So do you notice anything about this function right here and its derivative, which is right here? Well, guess what? They're the same thing, and you already knew that the derivative of e to the x is e to the x, so that just confirms that this looks like it's probably the correct thing to do, and in fact it is. So because they're polynomials, we can take the derivative of them. So notice anything interesting? Yes, they're the same. And again, that's because the derivative of e to the x is e to the x. Okay. All right, another look at convergence. So we've looked at like 0.33333 converges to 1/3. We looked at that square where we cut it in half and added up the areas of 1/2 plus 1/4 plus 1/8, and that converged to 1. This is another look at convergence. So an alternating series, which is one of the ones that you do need to know for the test that they are testing this year, is a series where the signs alternate between plus and minus terms. So consider the series 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9 dot 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 dot. That would be an alternating series. If I wanted to write the general term, since this is going up by 2's on the bottom, it's going to be 2n. I'm either going to adjust it by +1 or -1, so let's do -1 in this case. So if I plugged in 0, I would get -1, but I want it to be +1. So remember, the term that makes it alternate is -1, either to the n power or the n plus 1 power, depending on what makes it work out. So in this case, it looks like it's going to be n plus 1, because if I plug in 0, 2 times 0 is 0, minus 1 gives you negative 1, 0 plus 1 gives you 1, and negative 1 to the first is negative 1, and negative 1 over negative 1 gives me the first term is 1. If I plug in the next number of 1, negative 1 to the first power would be 1 plus 1 is 2, and negative 1 squared is 1, and 2 minus 1 is 1, so actually that's not going to work out, right? So if I adjust this by, say, plus 1, and I don't adjust that one, so sometimes if you can't see it right away, sometimes you have to kind of work it out. All right, so now if I plug in 0, anything to the 0 power is 1, and 0 plus 1 gives me the first term of 1. Now when I plug in 1, negative 1 to the first gives me negative, and 2 times 1 is 2, plus 1 gives me 3, so that gives me the negative 1 over 3 that I was looking for. If I plug in 2, negative 1 to the second power is positive 1, which gives me this plus 1, and then 2 times 2 is 4, plus 1 gives me the 5 on the bottom, so that would be the general term for this alternating series. Okay, so sometimes you got to kind of work it out to make sure that it works, so that's a good example of doing that. Okay. All right, so what does it mean to converge? So let's say here I start at 1. So we'll just pretend this is 1. And then I subtract a third. That'll make it bounce back here, right, to 2/3. So just pretend this is like a number line here. If I add 1/5, that'll bring it back here, but not as far because 1/5 is smaller than 1/3. And then if I subtract 1/7, it'll go like that, add 1/9, and it'll just bounce back and forth until eventually it's going to converge at some value on here. And I think the value this actually converges to is pi over 4, if I remember correctly, which is kind of weird, and series kind of do some interesting things. You wouldn't think that 1 minus third plus 1/5 minus 1/7 plus 1/9 would converge to something with pi in it, but it actually does converge to something with pi in it. Okay. Unfortunately, this year, we're not going to be able to see all that stuff because you guys are kind of getting the abbreviated version of series, but sometimes series do some things that you wouldn't normally expect. All right, so as far as the power series goes, you're going to have to be able to construct these, which is going to be in a future topic. So let's just introduce the types that there are. So a series with positive integer exponents, the 4 Taylor series you need to memorize, which in this case, this year you don't need to memorize, are all examples of power series. So the 2 power series that you're going to have to be able to construct are this: a Taylor polynomial and a Maclaurin polynomial. They're the exact same thing except Maclaurin's centered at 0, so it's really technically like x plus 0 or x minus 0, which is just x raised to a power. A Taylor series would be centered someplace other than 0, so for instance, if you were centered at 2, this would be x minus 2 raised to a power. So when we have some kind of Taylor series, so let's say we just have 4x plus 3 raised to the power n, I know just by looking at that that's centered at x equals negative 3, because negative 3 plus 3 would be centered, or would be 0. Or another way of looking at it is, and probably a better way of looking at it is doing the shifts that you learned in Algebra 2 and Pre-Cal. X plus 3 in parentheses is a shift that's 3 to the left, which means it's centered at negative 3. Okay. And again, that's the only thing that's important about is what it's centered at, which sometimes is important. Okay. All right, the rest of this is review. So is the geometric series represented by the summation of a r to the n minus 1 a power series? Well, that depends on what r is, so that depends. It could be if r was equal to, say, x, or x plus 2, then it would be a power series. Okay. But this is a geometric series. So what is the interval of convergence of the geometric series? Well, remember, geometric series converges when the absolute value of that ratio is less than 1. Can you always find the sum of a geometric series that converges? Yes, the sum is going to be this formula, which is a1 over 1 minus r. And remember, you can only use this formula when r is less than 1 and it actually converges. Don't try and use it when it diverges. So for a power series, the power series will either converge for all values of x, it'll converge on some finite interval, say from negative 1 to 1 or negative 2 to 2, with the same center as the series, or it converges only at the center itself. And you'll be seeing a whole bunch of examples in a later topic on these. Okay. So generally speaking, for all series other than geometric series, the only question that you're going to need to answer is, where does this series converge? You'll rarely, if ever, have to find the sum to which a series converges. The only exception would be if you compare that to one of our 4 known series, which again, you don't have to memorize this year. Okay. All right, so that's topic 57, kind of the abbreviated version. And we'll be moving on to topic, I think we're going to skip to 59 next.